Hello friends, this is part 6 of Electricity and Magnetism paper solution of Guwahati University 2022 Physics Honors. Okay, I have already made 5 parts and links are given in the description box. Because I can't complete this complete paper, I can't complete this paper in a single video. That's gonna be very long. That's why I have made many parts. So here you see. Before we start, please subscribe the channel and also hit the bell icon so that you get notified when new video will be uploaded, and when the next part will be uploaded, that's going to be appearing at the end of this video, at the end screen. So now, and also share with your friends if you think these videos are helpful, okay, and help me to grow my channel. So we are very close to 1K, so just help me to get that mark. So thank you for watching. Now let's start. So this is question number 4C. In the last video we have solved up to question number 4B. This is 4C. Here, state and prove Ampere's circuital law. Using this, find the magnetic field due to a toroid. That I will explain this. What is it? So now you see. So here is the statement of this Ampere's circuital law. It states that the line integral of magnetic field induction B around a closed curve is equal to the mu naught times the net current I through the area bounded by the curve. That is given by this mathematical expression, and here mu naught is the permeability of free space. It is a constant term. Okay, so let me explain. So here you see, let us consider a long straight conductor. This is a long straight conductor. Here you can see in this figure. So carrying current I and perpendicular to the page directed outward. So assume that way, assume this wire such that it is coming out of your paper, or if you are watching this video now, consider that it is perpendicular to the screen of your device and it is directed outward, right? Imagine that way. So now you see, according to the Biot-Savart law, the magnitude of this magnetic induction at the distance r from it, at a distance r from this wire, is given by this expression, right? So now you see, it is its direction is tangent to the circle of radius r. So if you want to find the direction of magnetic field at this point, suppose, then draw a tangent, right? And now question arises, if you draw a tangent, so how to determine that should be in this direction or in this direction, right? So that can be determined by your right hand thumb rule. Okay, so if you put your thumb along the wire and the remaining fingers will be warped around in this direction, so then the direction of this field in this way, right? So hope you have understood this. Now you see, the field B is constant in magnitude. The magnitude of this magnetic field is constant at all points on this circle. Okay, doesn't matter you are calculating the magnetic field here or here, so magnitude will be same, only direction will be different, right? And it is parallel to this element dl. So what does this dl means? Suppose we have considered a very small length element on this circle, then that is, we used to call it dl, right? And this tangent, obviously it will be parallel to this length element, right? Very small length element. Now you see, we have, if you integrate this field along this circle, line integral, so dl is the line element, length element of this circle, then what we're gonna get? So b vector dot dl, so that's gonna be given by b dot b dl cos theta. As I have already mentioned that this b vector and dl, these two are parallel, right? So therefore angle between them must be 0, and cos 0 is 1, so that's why we can write b dl. So here line integral b dl, so b is constant at each point on the circle, so it can be taken outside the integral. So here integration dl we have. So if you integrate this whole circle, then you will get the circumference of the circle, that is 2 pi r, right? And here you see, substituting this value of b from the above equation. So if you use this value here, right, then you will get this. Okay, so this 2 pi r cancels, so we have mu naught I. So this is the Ampere's circuital law. Line integral b vector dot dl vector is equal to mu naught times I. So here this I is the current through the area enclosed by this circle. So hope you have understood this. Now let's move on to the next part of this question. What was the next part? Here you can see this is the question. We need to find the magnetic field due to a toroid. Okay, so now let me tell you what is toroid. Suppose you have a solenoid. This is a solenoid, very long solenoid, and if you bend this solenoid in this form like this, so then it will be called a toroid. Right? So here you see, let us consider a long solenoid bent round in the form of a closed ring. This is, so here you can see the dots and cross, that means these are the loop of the solenoid. So hope you can get it, right? So by the symmetry, the direction of magnetic field B at any point is tangent to a circle, that is already we have discussed, right? Passing through the points and concentric with the triad, and the magnitude of this B is same at all points on any such circles, right? So now you see, let us consider a circle through a point P. So we have taken a point P here. You can see this is the point P. This is the point P. Okay, we have taken. So this is between the solenoid. This is the solenoid, suppose, and this point is in between this loop of this solenoids. So hope you have understood this. So now, and here you see, this R is the radius of the circle. Okay, so here you can see this circle passing through this point P, right? Its radius is smaller. So here it is written, hope you can see it, this is smaller, right? The small circle, this circle passing through this P is represented by this dotted line, right? Now you see, if you apply the Ampere's circuital law, you should get this, right? So suppose this is the one loop of the solenoid, yes, one loop of solenoid, considered that way, and this is the circle that we have considered of radius r through the point P, right? Then according to Ampere's circuital law, here you see the magnetic field at any point on this circle, that should be equal to mu net times of the current through this ring, right? So that's why I have here you see I have considered that the current through the solenoid is suppose I naught. Let me consider that way, right? Let me consider I naught. Then if there are n number of loops, right? If there are n number of turns like this, okay, then what will be the total current through this circle enclosed, through this area enclosed by this circle through the point P? If there are n number of rings, then total current will be n into I naught, right? I naught. Let me write it only I. So then according to Ampere's circuitry law, that is given by this expression. This is suppose equation number 1. So if you replace this I by n I naught, then you're gonna get this expression here. Let me then you see, you can write instead of mu naught I, you can write mu naught capital N I naught. You can write this, right? Now you see, as I have already explained in the first part, that B dot del dot product of this vector, that will be B dl, as these two vectors B and dl are parallel, right? Are parallel, so that's why theta will be 0, cos 0 is 1, so that's why we have got, and B is constant, so it is taken out, and integral of dl, that will be the circumference of the circle. Here we have taken the radius is smaller, so 2 pi smaller, right? So now here you can see, if you use these two equations, equation number 1 and equation number 2, so here integration of B dot dl is equal to B 2 pi r, and again this is also equal to mu naught I, which means mu naught n I naught. Then you will get this result, right? From 1 and 2, from equation number 1 and 2, you're gonna get this result, right? So from here, what you can write, you can write B is equal to this expression, right? If you simplify this result, yes. Now you see, if this 2 pi r, that means this circumference of the circle passing through the point P, let it be L, the circumference of the circle that is passing through P, that we have assumed through this point P. Here you can see, through this point P, this circle drawn in dotted line, its length be suppose small l, then this expression can be written as, let me go to the next slide, this way, right? So I have replaced this 2 pi r by L, right? So this is the required magnetic field, right? Now you see, if you find magnetic field at this point, suppose this is the toroid, right? If you want to find magnetic field, want to find any point, this is the toroid, this is the point, suppose Q, and if you imagine a circle like this, then the magnetic field at all the points like Q lying on this circle will be 0, because no current is being enclosed by this circle, right? So hope you have understood. And P was taken inside this, right? So that's why you can see the circle drawn through this P, there is current through the area enclosed by this circle. That's why we have got magnetic field here. But here at the point, at any point on this circle, which is inside the toroid, will be 0. So next question is, find the divergence and curl of magnetic field. So first let us find the divergence of magnetic field. So now you see, according to Biot-Savart law, we get this result, right? Now let us integrate this. If you integrate this, then you're gonna get B mu naught by 4 pi, which is a constant term, its value is given here, and integration I dl vector cross r vector divided by r cube, right? So now let us integrate this integral form of Biot-Savart law. This is the integral form of Biot-Savart law. From this equation, the divergence B is now let me write in the next slide. Okay, so now let's find the divergence. Okay, so here you can see divergence of this magnetic field B which can be obtained by mu naught I by 4 pi integration divergence of dl vector cross r vector by r cube, right? So here we're going to use a vector identity. Let me write that one. So now here you see we're going to use this identity here. So consider, here you can see, consider this r vector by r cube as c and dl vector as a, right? So let me clean these things. So if you do so, then what you're going to get this result, divergence b, and on the right hand side you're going to get, first let me do one thing. Just let us find this part only. First let us find this part. This is suppose equation number 1. So we can write divergence dl vector cross r vector by r cube, right? Let us find this one first. So here you're gonna get r vector by r cube dot curl of vector dl, right? Then minus dl vector dot curl of vector r by r cube, right? Vector r by r cube. So here you see this dl vector is a constant vector. So that's why here you can see the curl of dl vector, that's going to be equal to 0, right? It is going to be equal to 0. So since dl is a constant vector, so curl of, so just write curl dl vector, that's going to be equal to 0, right? That means this whole term becomes 0. Now let's go to this part. Here you can see, so let me copy this step and let me go to the next slide. Okay, so here you see, now the curl of vector r by r cube, right? Curl of this, you can write this one as a minus curl, then gradient of 1 by r, right? Because grade 1 by r, you have to you must know this result if you have studied vector. So 1 by r, grade 1 by r, that's equal to minus vector r by r cube, right? And you must know one more result here, that is curl of gradient phi, that is equal to 0. If you know this result, so from here you should get this is also equal to 0. That means we have got the second term is also 0, right? So that's why, so let me write here, that's why we can write divergence of dl cross r vector by r cube, that is equal to 0, right? So here you can see, if you use this result in equation number 1, let's move on to previous slide. So if you use this result in equation number 1, that we have got this is equal to 0, if you put here 0, then what you're going to get, so using this result in equation number 1, what you're going to get, divergence of magnetic field B, that is equal to 0. So hope you have understood this. So in order to find the curl of magnetic field, first let me take the help of Ampere's law. So this is the Ampere's law, so let it be equation number 1. Now here you see, so now let us consider a region with current density J, right? With current density J, and it is closed by the curve C, and surface area is suppose S. So let me write here. So J be the current density. It varies at different regions. Okay, right, it varies different region. So now you see, then current I will be given current in this region, current enclosed by this region of area S will be given by integration, surface integral uh, current density J dot ds, right? So ds is the small area element, so ds is small area element, right? Small area element. So now you see, if you use this result, this is suppose equation number 2, so let us use this equation number 2 in 1. So using equation number 2 in 1, what we're gonna get? So then we're gonna get that integral line integral b dot dl will be equal to mu naught times surface integral j dot ds. Now let's move on to the next slide. Now let us apply Stokes theorem. Okay, now let us apply Stokes theorem. By Stokes theorem, what we're gonna get? So here you see integral b dot dl, that's gonna be equal to surface integral s curl b dot ds. So that's how we can transform the line integral to surface integral. So let us use this here, right? So then what we're gonna get? So this is suppose equation number 3, and so 3 implies, therefore 3 implies surface integral curl. So let me write it properly. Curl b dot ds vector is equal to mu naught times surface integral current density j dot ds. That's what we're gonna get, right? So now here you see, if you remove the integral from both sides, then our result gonna be curl b mu naught times j vector current density. So this is the curl of magnetic field. So hope you have understood this. So remaining questions will be solved in next videos. Okay, so stay connected and hope you have enjoyed this video. And if you have enjoyed this video, please subscribe the channel, share with your friends, and motivate me to create new contents for you. Just just leave comments in the comment box if you think that I need to improve, and if you need any help, just let me know in the comment box. And please let me please help me to grow my channel and stay connected, subscribe the channel. So thank you for watching, see you in the next video.